Our next speaker is Bishal Deb from University College London, and he is going to speak on continued fractions using a Laguerre digraph interpretation of the Fuata-Zeilberger bijection and its variants. Please.
Okay, so I'd like to begin by thanking the organizers for providing me this opportunity. So I'll talk about So in this talk, I'll first show you some continued fractions, then I'll show you briefly the Fuata-Zeilberger bijection, and then I'll show you some Laguerre digraphs. So let sigma be a permutation on n letters, and for every index I, compare I with sigma of I and sigma inverse of I. Then every index can be put into one of these 5 classes. So an index can be a cycle valley, that is, if it is smaller than both sigma inverse of I and sigma of I, and cycle peak, cycle double rise, cycle double fall, and a fixed point, analogously. You may have seen the linear classification where you compare sigma I with sigma I plus 1 and sigma I minus 1. This is a cyclic analog of that. So I have introduced 5 statistics. Let me introduce 4 more statistics. So previously we were looking at the cycle structure of a permutation. Now let us look at the linear structure of a permutation. So consider a permutation as a word, sigma 1, sigma 2, and so on. And an index I is called a record or a left to right maxima if sigma I is bigger than every sigma j for sigma j less than I. So you can think of it as a record in a tournament. Let's say there's a running race, and so you're creating a record if you're better than everybody who's performed before you. And similarly, you have the notion of an anti-record or a right to left minima. So you are smaller than everybody to your right. And now you can ask whether an index I is a record or not and an anti-record or not at the same time. Then every index can be put into one of these 4 classes. It could be a record anti-record. It could be an exclusive record, an exclusive anti-record, or neither. And if you are more comfortable with mesh patterns, then these 4 statistics are also occurrences of these 4 mesh patterns. So neither record, anti-records, these are occurrences of the pattern 3, 2, 1. Okay, so you have the 5 statistics coming from the cycle classification, 4 statistics coming from the record classification. Put them together, and you'll have maybe 20 different statistics, but no, you have 10. 10 of them cannot occur. So for example, so these are all the 10 different statistics. So there's this classification into 10 different types. So notice that a record anti-record can only be a fixed point, for example. And the cycle valley can be an exclusive record or a non-record anti-record. Okay, so I have introduced 10 different statistics. Consider this 10 variable polynomial enumerating all of these 10 statistics simultaneously. Then Alan Sokal and Zhang Zheng found this beautiful Jacobi type continued fraction enumerating all of these 10 statistics. And this was in a recent paper, and they proved it using a bijection due to Dominic Fuata and Doron Zeilberger going back to 1990. So now, however, we did not count the number of cycles. So consider this 11 variable polynomial now, all the 10 previous statistics and the number of cycles. If you put this on your computer, you'll very quickly see this does not have a nice continued fraction. But if you specialize y1 equals v1, that is, you forget the record status for cycle valleys, you have this continued fraction. Your computer will tell you this. And so Sokal and Zheng, they conjectured this continued fraction. They weren't able to prove it. However, they proved it using 2 specializations. So you specialize y1 equals v1 and y2 equals v2. So you forget the record status of 2 of the different things. Then they could prove it, but they call this their second J fraction, and they used a different bijection, which is due to Philippe Bian from 1993. And this is the twist in the story. I can prove their full conjecture but not by using the Bian bijection. So far, whenever people find continued fractions counting the number of cycles, it typically involves the Bian bijection, or maybe Fuata-Zeilberger and you do Fuata fundamental transform, whereas I will count number of cycles using the Fuata-Zeilberger bijection. And I'll show you how we can do that. So let me give you a very concise overview of this bijection. So I'll now describe a few sets. So first of all, let F denote all exceedance indices. So these are all indices I, such that sigma of I is bigger than I. And then you have exceedance values, sigma of I is bigger than sigma inverse of I. So you don't need to remember these right now, but let me just tell you, you have these 5 sets. So you have exceedances, indices, and values. Then you have anti-exceedances, indices, and values, and fixed points. The insight that Fuata and Zeilberger had was that they noticed that a permutation can be described entirely by the following data. You need to know what are these sets F, F prime, G, G prime, and H. And furthermore, this permutation, when you restrict it to the set F, it's a bijection between F and F prime. And when you restrict it to the set G, it's a bijection between G and G prime. So if you give me these 3 pieces of information separately, you can describe the permutation, you can construct the permutation back. Using this information, using this strategy, they constructed this bijection between permutations sigma on one hand, and on the other hand, there's this pair where omega is a Motzkin path. So it's a path where you have rise of unit rise, level step, and a fall. We'll see an example in a while. And the level steps come in 3 different colors. So this is slightly different from the original bijection of Fuata and Zeilberger. This is the variant of Sokal and Zeng that I'm using right now. And they showed that the description of this Motzkin path can entirely describe the sets F, F prime, G, G prime, and H. So you have one part of the data that you need. Furthermore, this path also has some labels associated to each of the steps with some rules. I'm not going to tell you what they are, but then the labels describe these restricted maps, these 2 bijections. And so let me now give you a quick description of the Motzkin path. The Motzkin path is easy to describe. It's simply if if index I is a cycle valley, step I is a rise, index I is a cycle peak, step I is a fall, I is a cycle double rise, double fall, or a fixed point, step I is one of the 3 level steps. And this is the description of the labels. It is there on my slides if you want to take a look at it later. But let me go to an example. So here we have this permutation, and I've written it in cycle notation as well. So you can see that 1 and 3 are cycle values. That's because 1 is smaller than 7 and 1 is smaller than 2. So 1 is a cycle valley. 3 is a cycle valley as well, because 3 is smaller than 5 and 8, and so on. And 4 is a fixed point, clearly, etc. And so the Motzkin path is described. So as soon as you have this information, you can construct the Motzkin path. So for steps 1 and 3, you have rises. Steps 7 and 9, you have falls. And all the other steps are the 3 different colored level steps. And this is how the labels are. I have just written the labels here. So this is the set F, F prime, G, G prime, and so this is I, and this is sigma I. So one way of, if you are familiar with inversion tables, then these labels, they are actually describing inversion tables. So this 1 here means that to the left of 5, there is exactly 1 of the letters which is bigger than 5. And the 1 here represents that to the right of 6, there's exactly 1 letter which is smaller than 6. So this was their insight, that if you take inversion tables in 2 different ways, you can construct this bijection. And now I'll tell you, okay, so now the puzzle is, can you recover the number of cycles in this construction? It is not clear at all. I say that if you give me a permutation, or if you give me the Motzkin path and these labels, I cannot recover the number of cycles, but I can count them. for a fixed Motzkin path. So let's take a look. So now the protagonist of our story comes in. So a Laguerre digraph of size n is a directed graph on vertex set 1 through n. Each vertex has in degree 0 or 1 and out degree 0 or 1. So this is an example of a Laguerre digraph. So here you can see 5 has in and out degrees 0 and 1. Everything here has in and out degrees 0 and 1. 8 has in degree 0, out degree 1, and so on. And very quickly you can see that a Laguerre digraph can only have two possible types of connected components. You could either have directed cycles or you could have directed paths. And hence, these generalize permutations in two different ways. So if you have no directed paths, then that's the cycle structure of a permutation. If you have only one directed path and no directed cycles, that's a permutation written as a word. So they generalize, and these objects are analogous to the Laguerre configurations which are developed by Fuata and Strel to describe the coefficients of the Laguerre polynomials. That is why the name Laguerre digraph. So now I will describe a history of the Fuata-Zeilberger bijection. So we start with a graph that has n vertices and no edges, and we have 3 stages. In the first stage, we insert edges. So at every stage, we insert edges I going to sigma I. But the crucial point is, we do it in a particular order. So first we insert all the fixed points. So every I in H is inserted. That is stage A in increasing order. Then we insert all I in G in increasing order. And finally, we insert all I in F in decreasing order. And we analyze this process carefully, and we can see when cycles are formed in this process. So let's take a look. So this order is suggested by the inversion table, and there are well-known algorithms for obtaining bijections back from the inversion table. So let's take a look at this. So we have the same permutation as we had before. The set H is simply 4. And these are the inversion tables. So so we begin with a graph with no edges and all the vertices, and we insert one edge at a time. So first stage, we insert all the fixed points. So at the end of the stage, you insert 4 and you just have one loop. And you don't have any non-trivial cycles or non-trivial paths at this point. Next stage, we insert edges I to sigma I from G, and I goes in increasing order. So first we insert 2 goes to 1, then we insert 6 goes to 2, then we insert 7 goes to 6, then we insert 8 goes to 3, and then we insert 9 goes to 8. And notice that at the end of this stage as well, you have loops, you have some directed paths, but you don't yet have any directed cycles. The directed cycles will come now at this stage. So we insert I goes to sigma I in decreasing order of I now. So first we insert 5 goes to 9, no cycle yet. 3 goes to 5, we have one cycle. And 1 goes to 7, we have our other cycle. So the point is, we carefully analyze this process and we can count when cycles, so the cycles can arise only in stage C. And we can count how many of them are there. In fact, we can show that so you have several different possibilities for, so for fixed sets F prime, you have several possibilities for the labels. And among all the possibilities, there is exactly one that will construct a cycle. So we can count the total number of cycles if we sum over all permutations with the same Motzkin path. So this resolves this conjecture of Sokal and Zeng for permutations. In fact, our approach also leads to another conjecture going back to Arthur Andriano-Rivoni and Zhang Zeng from 1996. So they had a 4-variable conjecture counting different statistics on objects enumerated by Genoki numbers. So I have managed to resolve that as well. And in the paper of Sokal and Zeng, their most general continued fractions have continued fractions with infinitely many variables, infinitely many statistics. So in the same flavor, I have also done that. And thank you.